have major impact on the final outcome. So these are the ways you can identify and you can do the feature selection. Correlation analysis, we have two major statistical measure. One is the chi-square test, and another one is called correlation coefficient, also known as the Pearson coefficient. This is the example. I am not going to discuss this example now because we are already running short of a time, and so let me skip this. Now see, this is the graph that I generated for the two features. From this graph, if the two attribute, in this case, the first graph, in this case, if two attribute have this kind of a plotting of scatter plot, then we can say that the attribute on x-axis and attribute on y-axis are correlated because there is a pattern, and that pattern is increasing. If you feed this data using the linear regression, we have a straight line, and that is increasing. So that is called positively correlated feature. In this example, this case, again we have a straight line, but here the line is decreasing, and that's why these two attributes are correlated, but these two attributes are negatively correlated. When one increasing, the other one is decreasing. So that's why they are the negatively correlated. In third graph, if we start from the value of x from 0 to 1 point, let's say the at x is equal to n, we have an increasing pattern. After the value of n, x is equal to n, we have a decreasing pattern. So here the attribute on x-axis and attribute on y-axis are related, but up to the x is equal to n, the both attributes are positively correlated, and after that, those attributes are negatively correlated. These are some of the examples, some of the scatter plot where both the attributes are not correlated at all. Now, why this is important? Because if the two attributes are correlated, that means those two attributes have high impact on final predictions of the model. So you have to find out if two attributes are very strongly correlated, you need to remove those attributes, because otherwise what happens that the algorithm your model, machine learning model may bias towards those two attributes. This is the visual evaluations of correlation, where the scatter plot ranging from -1 to 1, the -1 and 1 are the correlated, and then in the other case, if it is a 0, then in that case, the both attributes are not correlated at all. So we have to keep those attributes in our final data set. The second operation is feature creation. In case of feature creation, sometimes we need to create new feature in our data set. Now, why this is important and how it's impactful? Let's see. Here is the 2D distributions of cancer data set. If we look into this image, we cannot conclude that here we have two classes, and we cannot conclude that whether these two classes are separable or not separable, or from this 2D distributions graph. But if I convert this 2D graph into the 3D graph by introducing the third dimension, third features, then my graph will look like this. And here you can see the clear separation line between the two classes. This is class 1 and this one is the class 2. So in 3-dimension space, both the classes are linearly separable, while in the 2D case, both the classes are overlapped on each other. So why it is important? Because suppose, for example, if you are working on a support vector machine, then in that case, if you apply the support vector machine where the class is overlapped, then it faces difficulty in finding the linearly separable line. So there must be, in that case, you have to apply the kernel function. But if you don't want to apply for kernel function, you need to just convert the 2D data set by introducing the new dimension and convert that data set into the 3 dimension. So in that case, there is a linearly separable line hyperplane is there, and where an SVM can utilize this and can perform with good performance accuracy. Now let's visualize this thing. Here is a small video which depicts how the 2D data is converted into the 3 dimension and how we can visualize the clear separation line. So here we have a 2D data. When I rotate this cube, we have a clearly visible separation line. So that's why the number of dimensions are very much important for the training of machine. Because if we convert the 2D into the 3D, we have a clear separation line, and then we can utilize that for our machine learning algorithm. This is one of the data set. This is the second data set. So you can clearly see that at upper part there is a one class, and at the lower part, and if I convert that into 2D, there is a no separation line. Both the class are overlapped, and in that case, the machine learning algorithm cannot perform well. But if we increase the third dimension, then there is a clearly separation line, and at that point, machine learning algorithm can get the benefit of that. So here are some of the 3-dimension and 2-dimension view of some of the data set. So here we have 3 classes. In 2D, we cannot identify any separation line, but if we plot this data into the 3D, then we have a clear separation line between all 3 classes. Same is here. We have a clear separation line again for the diabetes data set. This is for the cancer data set. We have a clear separation line. And you won't believe that if you apply any algorithm on mammography data set, then that algorithm, the maximum accuracy that you can get is around 30–40%. Because of this reason, the class is highly overlapping, and the class is imbalanced. The data set are imbalanced. Means there are the one classes which is in very less number, so that it is not possible to from any algorithm to detect that minority class. So you have to, at that point, means when you face this kind of problem, you have to play with the feature engineering. You have to create some new features which can help to have a better accuracy from our model. The third operation is feature transformation and scaling. Machine algorithm often struggle with the data set where the features are on drastically different scale. For example, let's take salary data set. If out of 100 employee, the 90 employee have a salary of 10,000, and the rest of the 10 employee have a salary of 1 lakh, then that kind of a data set, the machine learning model cannot work well. We have to scale down the 10 salary of the 10 all the employees in the range of 0 and 1, or maybe some other range, because the machine learning models, if they have a very large range of the value, then it is possible that the machine learning model bias towards the values which are more in number, and that makes your machine learning model suboptimal. So for that, we have a certain operation. We can scale the attribute. We can normalize using min-max and Z-score normalization. We can discretize the data or the attribute, and then we can apply the smoothing by being mean or being median. In binning, we have to create the bucket. We have to discretize. We have to distribute the data into that bucket, and then we have to smooth the outlier with mean value of that bucket or median of that bucket. That way we can smooth the each bucket and then we can combine the data. So ultimately we have a smooth data set. Dimensionality reduction is one of the options which can transform your feature. And the polynomial features means you have a age and you want to transform that feature, then you have to just square the value of all the ages. So that way you can do the polynomial transformation of the feature. And that will help linear models to detect the non-linear patterns. Linear models, that means SVM or logistic regressions. So those are the algorithms which can get the help from the polynomial feature transformation. Now here, let me show you how we can apply the Z-score normalization using Python programming. So Z-score and min-max normalization are widely used to normalize the data. This equation is for the min-max normalization, and here I implement one code where we have a initial data, that is a synthesis data. We have a 5 values, and for the Z-score normalization, the equation of the Z-score is xi minus mean value of x divided by standard deviation of x. So here I implemented that, and let's run this and see. Let's see how it works. So the 70, 80, 90, 100, and 110 are now scaled down in between -1, -2 to 2. So we have a new value. So this way we can use the Z-score normalization to scale down the large numbers. Second one is the min-max normalization, where we have to feed the value, means we have to derive the new max or new min, that is the new range where we want all the data to fall, and we have to just place those value into this equation so that it will give us new value for each vi value. This is the example where we have a actual value 200, 300, 400, 600, and 1000, which we can scale down or we can normalize in between 0 and 1. The last one is feature encoding. Now, feature encoding is required because the machine learning algorithm works well on numeric data. Machine learning algorithms are designed to work on numeric data, in fact. So converting the categorical data to numerical, that we can do using feature encoding. There are different techniques of feature encoding: one-hot encoding, label encoding, and target encoding. Among from these three, the one-hot encoding is widely used. The process of converting the categorical or numerical data into the numerical format to ensure the optimal performance of ML algorithm that require the numeric input for training. Now let's see how these three methods can work. So suppose, for example, we have a for value in color attribute. That color attribute has red, blue, green, and black. If you use the label encoding is very straightforward and it's simple. We have to just assign the numbers. That means, for example, let's assign 1 to red, 2 to blue, 3 to green, and 4 to black. So in label encoding, what we have to do, we have to find out what are the possible distinct value in that attribute, and then we have to assign the value, the numeric numbers in each distinct value of that attribute. In case of one-hot encoding, we need to create the binary column for each possible value. This is important. We need to create binary column for each possible value. In this case, the possible value of color attributes are red, blue, green, and black. Means any data object in the data set have one value from this four possible value, from this four possible color: red, blue, green, or black. So in case of one for encoding, we need to create the binary column for each possible value. That means we need to create the binary column for red, blue, green, and black. So here you can see in this table, one hot encoding table. We have a for value. We create the first column called red. This is the binary columns. So it has value 1 when the original tuple has the value red, and the rest of the attribute have the 0 value. In the second attribute, or sorry, in second tuple, the original color is blue. So we need to set the column blue to 1 and rest of the columns are set to 0. Similarly, for green, we need to set the value 1 to green, and for black, we need to set the value 1 to the black column. So in one hot encoding, for one color attribute, there are 4 possible values. So we need to create the 4 binary columns. And for each tuple, only single column have value 1 and the rest of the all other binary column have value 0. This one-hot encoding is very useful in machine learning because it increases the performance drastically. In case of target encoding, the encoding depends on the target variable. So as we can see here in data set, I have a different feature, different tuples, and the target value is also seen here. So for the in target encoding, what we have to do, we have to calculate what are the red values, the 2 red values, and for that, those 2 red tuples, one target is sweet and another one is not sweet. We have a 2 class variable here, sorry, 2 class value here, sweet and non-sweet. So for one tuple where the color is red, the target value is sweet. For another data object where the color is red, the target value is non-sweet. So sweet is considered as for positive target class for the mean calculation. So here from 2 data object, the sweet is only 1, so that is 0.5. For blue, there are 3 data object here, and for those 3 data object of blue, there are 2 non-sweet and 1 sweet. So the encoding value is 0.33. In case of the green color, there are 3 data objects and the target value for those 3, 2 are sweet and 1 is not sweet. The encoding value is 0.66. For the black, both the data object belongs to the class sweet, so the encoding value is 4. So this way, target encoding is implemented. So encoding is very crucial because in case of image processing, and if you are dealing with the image data, at that time, even in the case of you have pixel value, which is a numerical value, even in that case, you have to do the one hot encoding to minimize the range of the pixel value. Dealing with the missing value. So for if your data set have a large number of missing value, in that case, we have to take certain steps. Either we can drop that attribute if that attribute is not important. If we think that the attribute is not have nothing to do with the target prediction, then we can straight away drop that attribute. Or if the attribute are important and we require the attribute, then we have to fill the missing value. To fill that missing value, we can take the attribute mean or attribute median. Now here, I want to show one of the research paper because I want to show you that my paper that was published in 2021 in Journal of Information Science and Engineering. Actually, I wrote this paper during the COVID time. At that time, actually, it was the beginning of the COVID-19. Sorry. So at that time, the data set I couldn't find any data set the COVID data set. I wrote lots of email to the Chinese universities and US university, but they won't help me. Finally, I got one data set for the COVID, and that data set has lots of difficulties. The original data set has 123 attributes and 5,644 instances. 123 attributes and 5,644 instances. During this research, my majority time was spent in data preparation, because the data set or the data is in worst case, because it is beginning of the COVID-19. At that time, it is very difficult to get the accurate data, but still I try to use this data. In this data set, from 5,644 instances, only 600 samples or data object contain some meaningful clinical information. And in that 600 instances, most of the features out of 123 features has missing value. Now you can imagine the amount of the missing value. So the data is totally sparse data. For certain attributes, there are 99% of the value is missing. So that means those attributes are useless. Because if the URI-related attribute have 99% of the missing value, I cannot replace those 99% of the value with the attribute main or attribute median, because that is meaningless. So what I did, I just straight away dropped that attribute. And I just keep the attribute which have which has less than 60% of the missing values. And all the attributes which have more than 60% of the missing values are all removed. Because if the missing values are more than 60%, then there is no meaning to keep those attributes. Even if I replace those values with the mean value of attribute, then it is injustice to the model learning. So after applying all these steps of feature engineering, finally the data that I have is only has 30 attributes and 600 instances. So that means from 123 attribute, finally I have a 30 attributes, and from 5,644 instances, I have only 600 instances which are the meaningful. And so after doing all these things, finally I'm able to publish my paper, and it was accepted. So I think in the last session, someone asked the questions that can we use the synthesis data set? So I want to actually comment on that. Yes, we can use the synthetic data set, but in that case, for primary use, we can do that. But at the later stage, we have to prove that we start with the synthetic data set, but we need to apply our model to some other data set as well, real life data set as well, so that we can prove that yes, it works on synthetic data set as well as it also works on the real life data set as well. So that way we can convince our reviewer or our examiner for our successful publications. So moving to the next slide. Can we automate these things that we discuss? And I think for the automation, lots have already been discussed in the last session. So I think nothing need to say about that, but still there is an AutoML platform available where you can automate all the feature engineering operation that we discuss. So that we are lucky actually right now, we are living in the decade where lots of things are happening in the AI and in machine learning, which makes our task easy. Now let me show you these things practically. This is the Titanic data set. We perform some operation on this Titanic data set. We are going to perform some operation on the Titanic data set. So Titanic data set is actually used to predict the survival and non-survival. So survival is our target variable, and we have other features as well. So let's start with Google Colab. Now I hope that my screen is visible. So I'm using the targeting data set. Yes. So first of all, let's get the data set using pandas. This is the URL from where I get the targeting data set. I just get the df variable and just display the data set information that we collected. Okay. So these are the features that we have: passenger ID, survival, E-class, name, gender, age, and all that. So once we have a data, the next task is to get the relevant features, handle the missing values. For the missing value, we can use for numeric data, we can use the mean value or the median. And for the categorical variable, we have to apply the one-hot encoder. So for that, we need to import some of the libraries. These are the features that we selected for our purpose. Okay. Straight away, I selected only 7 features, and this is the target variable that the survived. From these 7 features, 4 features are of numeric features and 3 are categorical features. So if we want to encode, or if you want to pre-process the data and we want to we need to apply, we need to replace the missing value, and for that we have a Python function that is called simple imputer. And the strategy is median. That means it will use the median of the attribute to remove the missing value. For the categorical attribute, we perform 2 operations using the pipeline function. The first step is simple imputer with the strategy most frequent. So most frequent value of the categorical attribute is used to replace the missing value. And in pipeline, the second operation is one hot encoder. So one hot encoder is applied here, which encode the categorical data convert the categorical attribute in the binary attributes. Once we complete that, we need to create the column transformer. In that column transformer, we apply the numerical transformer on numerical features. This is the numerical transformer. And categorical transformer, this is the categorical transformer where we perform 2 things: missing value and encoding. So the categorical transformer is applied on categorical features. These are the categorical features. Okay. Now we create the models. Again, in models, there are 2 steps. First step is to do the data pre-processing. So first step is preprocessor, and second step is classifier. And we use here random forest classifier. So what this pipeline function will do, whatever the data will pass into the model, first it is apply the preprocessor. Preprocessor, what is the preprocessor? Here is the preprocessor. So preprocessor apply the numerical transforming and categorical transforming. Okay. Once the data is pre-processed, it is passed to the second step, that is the random forest classifier. And it will train the random forest classifier. Still, here we just define the model. Now we need to fit the model. So to fit the model, we need training and testing data set. So here we create the train test split from our original data set, and then we use the model.fit to feed the random forest algorithm. Once it's done, we just bring here the accuracy scores. So it is already run. So let me show you that these are the attributes, and this one is the target attribute. Okay, the accuracy is 81%, precision is 78%, recall is 75, and F1 score is 77. Here we just select some of the features. We selected the 7 features and we got this accuracy. Now let's apply some of the feature engineering technique. So we apply the second feature engineering, that we create the two new attributes. One is called the family size from the existing attribute of sibling score and the parents score. So family size is defined number of sibling and the number of parents. We also create one more attribute that is called is alone. So that if family size is equal to 1, then that means that person is traveling alone in the Titanic. So let's see how this data set look like. So we have a two attributes here, family size and is alone. These two attributes are we created new. Now let's do the same thing. We now train our random forest on this new data set, and let's see what accuracy we will get. So in now the accuracy is 82%, precision is 81, recall is 75, and F1 score is 78. Let's compare both the things. In baseline model, that means in original data set, we have accuracy 81. When we create the new features, we have an accuracy of 82. So we have a clear gain here. In case of precision as well, in original data set, we have a 78, but now we have a 81. Recall remains as it is in both the data. And F1 score is also increased in newly created, newly engineered features. So here we have a clear, we can see, we can note here clear gain on the newly feature engineered data set. Now let's apply one more technique. We create one more column called title. Okay, and again, when we apply these things, let's see how we create one more columns. And now the performance, let's see the comparison versus the baseline. Now, when we add one more column, we have a decrease in accuracy, precision, and F1 score. Now, that means if when we create the new attribute, we need to check whether the attribute is going to put any value into the model performance. In that case, we need to create the new attribute. Otherwise, it might happen that if we create the straight away, if we always select to create the new attribute, it might decrease the performance of the machine learning model as well. So here we apply some of the things. Now back to the presentation slide. There is one more file I created to verify, to check how feature removal. Now we will check for the feature removal. Again, we get the Titanic data set. We have all the attribute that we created, new attribute. Okay, let's run this program. So for the new engineered features, we have accuracy, model performance with reduced feature. So here we remove two features, this sibling numbers and parents number. So we remove those two features from the data set. Here we can see the numerical feature reduced feature set is there is no sibling or no parents numbers. Okay, so we remove those two attributes and we train the model with the newly reduced data set as well. So here we can see when we reduce the features, again we have a good accuracy. Instead of 81, we now got the 82 accuracy. Instead of 77 precision, we got the 79 precision. Instead of 77 means recall is 7, and F1 score is again improved with 78%. So again, so here what I want to show you is sometimes when we create the feature, we have a good accuracy. Sometimes we need to remove irrelevant features and we can boost the accuracy. So thank you. I think it's already too late. Actually, I want to show you something about using the VECA as well, but I think we are already running short of the time. So here I just want to end. And if you have any questions, then please let me know. Yes, I think how can feature selection adapt when the data distribution shift over time? Or are there any reliable metrics to evaluate the quality of engineered features beyond model accuracy? Yes, there are lots of features. Again, let me tell you that the accuracy is not one of the parameters. We need to check what our problem is, what our problem statement is. For example, uh, if we are working on cancer data set, and if we are getting the accuracy of 90%, that doesn't mean that that training of model is good, because in cancer data set, the minority class is positive cancer patients. Means in cancer data set, only there might be 5 to 10% of the patients which are positive belongs to the positive class, and all the 90% of the patients belong to the negative class. So that means if your model is claiming the 90% of accuracy, that is maybe due to the accurate prediction of the negative class. But in the cancer patient data set, the negative class is not important, because the misclassification cost of the negative class is maybe some expense of some more rupees to get some more testing. But the misclassification of the positive class may be result into the life loss. So the misclassification cost, when the misclassification cost varies very drastically, at that time we need to go with the other parameters. And to answer you the first question, that the feature selection adapt when the data distribution shift over time, no. If the data distribution shift over the time, again we need to recheck.
Do you have any other query?
So at that time, we need to recheck the training of the models, and we need to check if the data set is drastically changed.
Thank you, sir. Anyone else is having any query? Participants? Okay, sir. So I guess there is no more query in chat box. I cannot see any other query. Thank you, sir, for delivering the valuable session. And definitely this session will help the fellow researchers and all the participants to understand why data pre-processing is important and why feature engineering is even more important. Right? Many times it happens that when we deal with the raw data, the model might not perform well, but when we go for the feature engineering, the results might be surprising. So the session will definitely help those who are working in field of model development. Thank you for delivering a wonderful session. Thank you, sir.
Thank you very much,
so
sir.
Here we are concluding.
Yeah, congratulations from my side for organizing such a nice event. And actually, the last session was very good, really very good. Actually, I also attended, I think, 30 minutes of the show, but it was very good, sir. So I just congratulate the entire team of GEC Modasa, sir. Thank you.
Thank you, sir. Thank you.
Thank you, sir.
So participants, we will meet at our regular time tomorrow. That is 6 p.m. So we can leave the meet. Thank you all.
Thank you, sir.